less decent, even though there is still a lot of things that we can do with this, is about the first talk that Carmen, the first lecture that Carmen gave. So that's why I decided to call my presentation Stochastic Animal Farm, because we are going to only see things about animals. Indeed, only 2 exercises about animals. So first of all, I'm going to talk a little bit about the bees. So I don't know if you remember, but let me refresh your memory a little bit about the problem. So we have some bees that are deciding whether to go to spot A or to spot B. And we will assume that these 2 spots are more or less the same, but it's a parameter that we can adjust in the model. And the thing is, like, the bees are undecided. Some of the bees are undecided, so they are like, I don't know if I should go to A or should go to B. Then at some point, they can adapt an opinion of another bee, either A or B, and then they will start dancing. So they will start dancing for a while. The length of the time that they will spend dancing depends on the quality of the site. That's why we have these parameters here, no? And at some point, they will return to the undecided state. So this is basically the problem that we want to solve. We will just put some rates here. So the rate at which 1B copies strategy A is just 1 parameter lambda. Same for here for copying the strategy B. And these 2 rates, in general, it can be different, but in a while I will just set them to the same constant. Okay, so now I'm going to use a Gillespie algorithm in order to simulate that. If you remember, Carmen also said that you can do this another way, and I know that some of you have done it this other way, but let me stick to Gillespie. So Gillespie, well, let's do a fresh reminder of how Gillespie works. So first of all, we need to compute the total rate for a change. So this is everything that can change. So we can either have one undecided B copying 1B with strategy A, the same for B, and then the rates that they become undecided, which are this one. So then, once we compute this total rate, we compute the time until something happens. So the time until something happens is given in this way. So you have to keep in mind that this time will change as we change the rate, and it also depends on some random uniformly distributed number. So this time will change from simulation and from time to time. So this is sort of problematic, but I will later explain how I fix that. And then we know that at this time something has happened. That's nice, but what has happened? Then in order to do that, the typical thing that we do is, okay, we throw a random number between 0 and W, and we see in which of these boxes we are in. So for instance, here we throw this random number, it tells us here, and we say, okay, this is in the blue box. So one undecided B is going to copy strategy B. And this is the basic idea behind a Gillespie algorithm. So this is what we will do. And now the problem. The problem is that if you look at a trajectory, you will see something like this. We have like some number of bees. Let's say that this n is the number of bees with a strategy A. It doesn't matter, no? You have it until some time, T1, and then it changes. But this time difference are changing from time to time. And indeed, if you run the same simulation several times, you will find that the times are different and it's hard to do an average. Well, not hard, but you have to be cautious about doing averages. So how do we solve this? We can just discretize time in some sort of bins of width h, which is a parameter that we can decide. And then the value that we will assign to each of these bins is not anything more fancy than a weighted average of how long the trajectory stay here, plus how long did the trajectory stay here, plus how long did the trajectory stay here. If you are interested in doing a Gillespie and you want to do these things and you need some help, I can give you the algorithm. I have it in C++ and in Python. Okay, so just keep this in mind because it's very important, and also every time you average things badly, a kitten dies, so we want to save the kittens. Okay, and let's jump to some results. So I just did a simulation. I started with the same amount of bees with strategy A and bees with strategy B. And I let the equations evolve. And the nice thing that we were able to see here is that even though I am putting that the two sides are exactly equal, so that they are equally good, the bees are able to decide. And they're able to say, okay, let's move to this place. This is a nice effect because, of course, the bees don't want to get stuck at I don't know where to go. They need to move to some place eventually. And as you can see here, at some time, the total number of bees that has chosen one strategy reaches a sort of meta-stationary state, let's say, and it stays there, and then at some point, there is one strategy that goes extinct, so it goes to an absorbing state, and all the population has just one opinion, which is nice. And then another thing that we can do is to see how this sort of meta-stable density of bees that have one strategy evolves as we change the parameter. And there was also some theory that we can do here, like you can write the deterministic equations and get some theory, some dynamical system analysis. I believe.
Why do we have these fluctuations once they equilibrate? All the bees are going.
Yes, this is because that's a good question. This is because there is still. I am not plotting it here. Maybe I should have added here, but there are also some undecided bees. So what is happening here is that some bees that have this bee strategy are going to an undecided state, and then they are coming back. And indeed, it could happen that if you get not very lucky, and in time, if you give infinite time, at some point it could happen that all the bees become undecided, and then they will reach an absorbing state and stay there forever. So the stationary distribution is just everyone is undecided. But in a realistic time, you will not see that. At least not for a parameter which is far enough from this point over here. Okay, and then we can see how this density evolves, and it is exactly what we got from the theory. I don't know if you remember, but when this lambda divided by r, which is just 1, so it doesn't matter, is smaller than 1, we just have like not a decision. They just reach the undecided state. But then as we increase lambda, we get some fraction of the bees to be in one state, which this density is also, you also have to keep in mind that this density will be only A or only B. They will just decide one place, and they will probably eventually move there. Okay, so this is all that I wanted to say about the bees. And now let's move to the fish. So my idea for the fish was also very similar. So I will have 3 states. I don't know. This was more a free exercise that I was like, oh, maybe this will be cool. So we have inactive fishes. So they are fishes that are like not moving or not really moving. These are some active fishes which are actively moving through the media. And then I also decided to add a drifting fish, which is a fish that has some velocity, but it will stop eventually and become inactive. So these are the rates that I have included. This is very similar to what Fernando has explained today, and it was an amazing talk. I have to admit that I was not aware of this when I started this exercise. So probably it's a little bit worse than the model that you have seen today. But okay, let me just explain it a little bit. So first of all, I will just say, okay, one inactive fish can randomly decide to move in a random direction and become active. Then one inactive fish can copy the strategy of one active fish and become also active with some given rate. And then the last thing is that one active fish, I don't know why I'm pronouncing always wrong, can, with some rate, become a drifting fish. And then, just because I wasn't able to play a lot with the parameters, I decided to put here a delay. So this drifting fish will just stay drifting for some time, and then it will become inactive. So this is, a little bit nasty because we are losing, this is no longer Markovian because it also depends on some time in the past. But still, we can get a sort of generalized master equation and we can apply a modified Gillespie algorithm. So I was like, okay, I can deal with this. And then I decided to add some dynamics to this thing. So basically, I decided to add some bit check dynamic, but without taking into account the space, because I didn't have time for that. So they interact all to all, and I don't care about the space. They just copy the angle, the average angle, if they are inactive or they are drifting, and their velocity changes in that way. And then when they are active, I assume that they keep a constant angle and they have some propulsion, so they are actively moving through the media. And the only thing that I also needed to add is, okay, when an inactive fish becomes active, so when this reaction takes place, I will just assign a random angle to this fish. And when one fish is copying another fish, so in this reaction over here, I will just say that they will imitate sort of the average of the active species plus some error. I mean, the dynamics probably can be better, and if we want to do some analytics, probably we should do some things a little bit different, but it was just a random idea. Then let me explain a little bit how did I modify the Gillespie algorithm to be able to deal with this delayed reaction equation. So the idea is almost the same as before, but now I will keep a list of all the delayed reactions. So this is a list at what times I should make a drifting fish inactive again. So I will keep this list, and I will repeat the same process. I'll compute the total rate, compute the time until something happens. But then, if in this interval there is a delayed reaction that is supposed to happen, I will execute the delayed reaction, so a drifting fish will become inactive, and I will update the time to this time, to the time that this delayed reaction was supposed to happen. Otherwise, regular Gillespie, so the same thing, with the only exception that if a fish becomes drifting, I will schedule a delayed reaction at a time t+2. So very simple. Here you have some papers on reference in which they explain a little bit better this method and also a little bit about the generalized master equation that you can use to deal with these kind of problems. And let me move to some results and I'm done. So as you can see here, I just randomly adjust the parameters because I was also not looking at real data. So maybe that will be a nice thing to do, I guess. And as you can see, my goal here was to obtain some sort of peaks of high activity and then some times in which the fish are just stopped. And this is what I got. And then you can see how the modulus of the velocity, the average modulus of the velocity behaves and how the angle behaves. And of course, you can see that there stays more or less all pointing to the same direction because how I'm defining things. But then at some point, they will start jumping to a different orientation. And the velocity will have some high peaks, which correspond to these times over here. And that's it. That's all that I have done, and that is like good to talk. So if you have some question about it or you want to discuss other things, I'm here to talk. And thank you very much for listening. Yeah. Yeah, I mean, it was yeah, probably the notation was not the best, but yeah. Yeah, exactly. I mean, probably it could be improved. Like, I didn't have a clue about active matter when I started doing this. I mean, I did, like, since I am not using the position for anything, I didn't keep track of the position, but of course, no, yeah, I mean, it will be interesting to track the position and then do the average, taking into account the relative position. But if you remove tau, yeah, I guess so. I mean, I guess that it depends on how you tune the parameters. Yeah, I think so. Yeah. To be honest, like I didn't have time to play with it. Like I did it on a rush in these days before today. So I have not enough time to play with it. I would also like to look at how can you compute analytical results for this sort of model. I will later look at that paper. I am curious about it.
It would be nice to see if the fish stay together in the physical space or if they disperse.
Yeah, I mean, I guess that probably you should do a more fancy thing to get that they are not dispersing and so on. This was just like a thing that I did in a rush.